Welcome to this explainer. I'm absolutely thrilled you're here because today we're going to unlock a truly foundational concept in computer science. Now, if you've ever looked at a block of code or an algorithm and just felt instantly overwhelmed, seriously, take a deep breath. You are in the exact right place. We are going to demystify an algorithm known as selection sort. We're going to take it from total chaos to perfect order, and I promise you, by the end of our time together, you'll understand exactly how a computer thinks when it needs to organize data.
Okay, let's dive into this. I want you to step away from the computer screen in your mind for just a second. Imagine you're standing in front of a giant, chaotic pile of heavy boxes, and each one has a different number on it. Your job is to put them in a perfectly neat line, from the lowest number to the highest. How would you naturally do that? Well, you'd probably scan the whole messy pile, find the absolute lightest, smallest box, pull it out, and put it right at the very front of your new line. Then you'd look at the remaining pile, find the next smallest, and put it second in line. Believe it or not, if you can picture doing that, you already understand the core logic of selection sort.
So here is our roadmap for today. We're going to cover 1. Sorting the messy pile, 2. How selection sort actually works, 3. When to use it, 4. Real-world applications, 5. Common mistakes and limits, and finally, 6. The logic behind the code. Part 1. Sorting the messy pile and defining the chaos. If you crack open a standard computer science textbook, you'll find a formal definition that looks something like this. Selection sort is a simple comparison-based sorting algorithm that selects the minimum element from the unsorted portion and swaps it into its correct position. Kind of a mouthful, right? Let's unpack that jargon. Comparison-based really just means the computer is looking at two items and asking one extremely simple question. Hey, is this one smaller than that one? That's it. The entire goal here is to build a sorted array, a neat, organized line of data by carefully selecting the correct smallest element at each and every step along the way. To really visualize this happening inside the computer's memory, imagine the algorithm conceptually splitting your data into two distinct groups. Over on one side, you have the unsorted portion. This is your chaotic, messy pile, and with every single step, it shrinks. It gets smaller. On the other side, you have your sorted portion. This is your neat, organized line, and with every step, it grows. The algorithm itself is simply a bridge, continually plucking the absolute smallest item from that shrinking chaos and carefully adding it to the growing order. Part 2, how it works, the 5-step loop. And this brilliantly illustrates the invisible logic happening inside the machine. It's basically a 5-step loop. Step 1, we start at the very first element in our list and we just assume, just for a moment, that it's the minimum. Step 2, we scan the rest of the unsorted part to find the true minimum, the actual smallest number. Step 3 is where the magic happens. We swap them. We take that true smallest number and physically swap it into that first position. Step 4, we move our imaginary boundary forward by one space because that first spot is now permanently sorted. And step 5, we just repeat the whole process for the second spot, then the third spot, and so on until the entire list is perfectly ordered. Part 3, when to actually use it and its ideal conditions.
Now you might be thinking, hey, this is so simple, it must be the best thing to use everywhere. Actually, not quite. Selection sort really shines under some very specific conditions. First, it works totally fine for small datasets. If you're only sorting 20 items, modern computers are so incredibly fast it really won't matter. But its real superpower is that second point, a minimal swap requirement. Remember those heavy boxes we imagined earlier? In computers, sometimes writing or moving data from one place to another takes a ton of power or even causes wear and tear on the physical hardware. Selection sort only makes one single swap per pass. Sure, it scans everything, but it only actually moves an item once it knows exactly where it belongs. That makes it fantastic for simple systems, and of course, it's absolutely unparalleled for educational purposes when you're first learning the basics.
Part 4, real-world applications. Now, what's really interesting about this slide is seeing how physical hardware constraints actually dictate our software choices. Think about embedded systems for a second. We're talking about the tiny computer chip inside your microwave or a simple digital thermometer. In those devices, simplicity matters a whole lot more than blistering speed. Furthermore, in severely memory-constrained environments, selection sort is kind of a hero because it requires absolutely zero extra space to run. It does all of its sorting right there in the original list. It doesn't need to create a temporary copy of your data, which is a massive deal when you literally only have a few kilobytes of memory to work with. Part 5, common mistakes and limits. Time to address the elephant in the room. Okay, so 1 million. Don't let that massive number scare you, but it represents the extreme limit of this algorithm's performance. Because selection sort has to scan the entire remaining list for every single item, the amount of work multiplies really fast. Think about it. If you have 10 items, it takes roughly 100 steps. But if you have just 1,000 items to sort, it suddenly takes a massive 1 million steps. It stubbornly does the exact same amount of scanning every single time, even if the data is already sorted before it begins. So the single biggest mistake developers make is just assuming it's efficient for large data sets. It definitely is not. When writing the code, other common pitfalls include incorrect minimum tracking. That's when a programmer simply forgets to update the index of where the smallest item actually is while the scan is happening. Another big one is executing an unnecessary swap. I mean, if the smallest item is already right at the front of the line, you don't need to swap it with itself. And lastly, just completely ignoring those performance limits we just talked about. Selection sort is a highly specialized tool, not a universal one.
Finally, part 6, the logic behind the code, mapping the steps.
So the crucial point is that the actual code maps exactly to the simple concepts we just learned. Don't try to read it like some impossibly complex math equation. It's really just a recipe. The computer creates a loop through the array, it carefully tracks the minimum value it has found so far, it compares it to new items as it goes, and finally, it executes a swap. See? It is the exact same logic you already mastered in your head, just written down in a way the machine can execute.
And there you have it. You've just conquered a foundational sorting algorithm. You understand exactly how selection sort turns chaos into order by meticulously finding the minimum over and over again. But as we saw with that stubborn million-step limit, what happens when companies like Google or Amazon need to sort millions or billions of items? Selection sort would quite literally take years to finish. So I want to leave you with this provocative question to spark your next learning journey. As data sets grow massive, what ingenious algorithms step in to take its place? There's a whole world of advanced optimization out there waiting for you, and now you have the foundational knowledge to go explore it. Thanks so much for joining me on this explainer, and keep learning.